So let's discuss some parameters, their relation to the surface quality, mechanical properties, and manufacturing time. If you remember from the previous slide, we said that the orientation of the part to be manufactured is important, the amount of support is important, the slicing thickness, the path planning, these are quite important steps in process planning in fused ceramic fabrication. So how they are affecting these properties, for instance, the mechanical properties, obviously orientation will affect the mechanical properties since we are printing the part layer by layer. Depending on the layers, the orientation of the layers, your part may have different, let's say, strength values in different directions. So in additive manufacturing, this is one of the biggest disadvantage. You will have anisotropic properties, and this is due to the orientation and the slices we are using. And then the support structures will be affecting the properties indirectly, since they will not be inside the final part. Just the thing is that they have connection to the main part, and this interface is affecting the properties, but not too much, and that's why it's written as indirect here. And then slicing, obviously slicing will affect the thickness of the slices. If you have thicker ones, then probably you will have less strength, but if you decrease the slicing thickness, you will have better strength. And another thing, path planning. Path planning will affect mechanical properties, whether you have 100% infill, whether you have just a single shell or 3 shells, they will all affect overall mechanical properties. And let's have a look at surface finish, the overall quality of the surfaces. Obviously, supports will have a direct effect on the surface quality since they have connections to the surfaces. While removing the support structures, you may harm the surface and increase their roughness values. And slicing again has an importance in the surface finish, since if you have, let's say, inclined planes, and once you have thicker slices, then you have a staircase effect. Assume that these are slices. Although this was the original plane, but once you do the printing, you have a kind of a staircase, and that staircase is visible if you have thicker slices. If you decrease the slicing thickness, then you have you cannot easily see the staircase effect, but in any case, regardless of the thickness of the slice, you will always have some amount of this staircase issue. And then path planning will obviously affect the surface quality. If you have irregular patterns, let's say inside and outside, they may be affecting overall surface quality. And then let's talk about the manufacturing time. As you see, they are all affecting the manufacturing time. For instance, think about this pen. If I print this pen in this orientation, then that means I need to have, I think, let's say 500 layers. But if I print it in this horizontal manner, with maybe just 20 layers, I can do the printing. If the number of layers is decreased, then you will have less printing time. So this is how orientation is affecting the manufacturing time. Then support structure is obviously affecting. If you have supports, then that means you need to spend time on the fabrication of supports. And slicing is another important issue in terms of manufacturing time. If you have less number of slices for the same orientation, that means you will have thicker slices and the fabrication time will be less. But if you decrease the slicing thickness, you will spend more time on manufacturing. Another thing affecting the fabrication time is that the path planning. If you have complicated paths, if you have none, let's say if your printer is here extruding material and then stop extruding and goes to another point, then start extruding, this will take lots of time. So we want to have a continuous pattern. If you have continuous interior, let's say printing, then that will decrease the fabrication time. So this is how the parameters are affecting such kind of mechanical properties, surface finish, and manufacturing time. So these are some typical support structures. We are with weird shape, as you see, and we may use accordion-like support structures. This is most commonly, or we may have tree-like support structures. And the thing is that if you have some overhanging regions, you need to support them underneath. Otherwise, that extruded material will be bended and may sometimes fall. So this will decrease the quality of your resulting part. And in fuselage fabrication, in the infill patterns are highly important. As we discussed, they directly affect the quality of the mechanical properties of the resulting part. And it's also the same for the shells. And for the supports, as we discussed while we were watching the video, we may use similar material for the support. Like in this case here, we have PVA material probably for the model, and also the same material is used for the support structure. But in some capable machines, capable 3D printers, they may have a second extruder for a special support material, like water soluble or some other easier materials. And the thing is that if you are using the same material for the support, then that means it's better you try to find ways to decrease the amount of support structure. Otherwise, you'll spend more time on the supports, and that may take lots of time. Instead of using similar materials for the support structure, you may use secondary material. In that case, obviously, you need to have two extruder heads. In the first one, you can do all the printing with a single extruder, but for using a different material as a support structure, you need to have at least two nozzles, two extruders to complete the fabrication. And it has an advantage that you can use water-soluble or other special materials, and that will decrease your post-processing. Make it easier to remove these support structures. We have some example here, as you see, Y, H, and T letters. We have a kind of a bridge here. If you actually adjust your printing parameters properly, you may not need to use this underneath support structure. But the thing is that this bridge should be quite smaller, shorter. And another thing is that you need to have proper cooling. If the material is cooled directly while it's being extruded, then you don't need to use support structure, but to make it, say, robust, it's better you may use such support structures underneath these bridges. On the other side, for this letter T, since it's not a bridge, it's a kind of an overhanging region, for sure you need to use support structure. Otherwise, we will see this result here. You see, it will be printing in air, and you have kind of a mess here, and you may not be happy with this printing. And obviously, if you are going to print these letters, then you don't need to use support structures. You can simply rotate them and simply print on the table. And that will also decrease the fabrication, but this is just for showing you the support structures. And we also need to use support structure for some inclined planes. I usually prefer to use support structure for the angles which are less than 45, depending on the reference plane. So if you have higher than 45, you don't need to use, but this is also another parameter which can be set in the CAM software. It's not a basic idea. Another example here, kind of a C is printed in this configuration, but obviously I can print this one again by simply rotating it on the plane without using any support structure. In here you see a kind of a slice for a C shape. You see we have field patterns, 3 different field patterns. The first one is about the shell, and then we have some interior field patterns. So what do you think? For which one we can have higher speeds? For the shells or for the interior? Are you there, guys?
For the shelf?
You say for the shells you should have higher speed?
Yes.
For the interior.
No, we prefer to actually have slower speeds for the outer boundaries for the shells, since that will be the region we will be seeing after the part is printed. But the interior region will not be visible, so you can do it as fast as possible. If the quality is low inside your part, no problem, but the quality of printing, fabrication should be as high as possible at the outer shells, since that will be the regions you're going to see after the part is printed. And you can obtain higher quality with low speeds, so that you can make sure that plastic is printed properly. So let's continue with the rest of this chapter. We said that CAM software are highly important. In that CAM software, we try to set parameters related with infill, or the type of shells, the number of shells, the slicing thickness. They are all done inside CAM software. And there are various infill patterns, infill percentages. You can always play with these parameters. And the thing about bonding is that if the distance between a layer and the upcoming layer is too much, then probably you'll not be able to bond the extruded material into the previous one. So that's why you need to keep the distance at the defined value and make sure that your current layers stick to the previous one. And we said that we can produce accurate parts, high quality parts at lower speeds. And another thing is that to make sure that the layers are bond properly, we need to have a slight overlap between the layers. And even if you want to have a 100% infill inside a layer, assume that this is the top surface of a layer, and if you want to fill the interior of this layer completely, then you may have again a slight overlap between these paths. If you remember, I said that each line has a width of 0.4, so you can keep the distance between these two lines less than 0.4. If that's the case, then that means you have slight overlap, and there will be a proper bond inside your part, and probably it will increase the density of the part and also increase the strength of your part. So in the CAM software, as I mentioned, we can define different infill patterns, even complicated ones. And at the outer side of the slice, you need to have a kind of a shell. And it's very similar to pocket milling operation. If you are aware of CNC milling or kind of milling operation, you start with the profile and then go inside that pocket and continue removing material. And for the infill patterns, we don't have a unique solution. There are millions of solutions for a specific case. Depending on your parameter, your CAM software will calculate a one and then represent that pattern with the help of G-codes. And the thing is that we always try to find a continuous one. Since if it's a continuous one, then that means you don't need to stop the extrusion and start it once again. If it's continuous, then you can simply start it once, and then once the pad is finished, once the layer is finished, you can stop the extrusion and go with the next layer. But if you have discontinuous, let's say pads, you need to stop many times your extrusion and start many times once again, and that will actually increase your manufacturing time and also decrease the quality of your prints. Another thing about the infill patterns is that in order to increase again the strength, assume that this is a kind of a layer if you have vertical, let's say, infill patterns for a specific layer, then for the next one, assume that this is ith layer and this is i+1 layer. It's better you have horizontal infill patterns so that that will be actually increasing the strength of your part. Any questions, guys? Since I will be switching to a different topic, a kind of a special cases in path planning. So you see a part here. This is somehow similar to your fourth mini project. A cube is given, as you see, and we have some 3D wormholes inside. And now what is done? Slices are taken, such slices. And as far as I remember, the slicing thickness was 0.2 millimeters, 200 micrometers. And then paths are generated for these wormhole diagrams. Since once you take the slice of a 3D wormhole diagram, the resulting slice will be a wormhole diagram in 2D. Let's draw the kind of a wormhole diagram here. So now this is a kind of a slice. And then what is done here is that this is my work actually. We try to find a continuous pattern for this wormhole diagram. So for that purpose, I actually used Eulerian paths. What is an Eulerian path? If you are given a graph like this one, is it possible to construct a cycle or a path which visits these edges exactly once? So this is a problem. We are trying to have a continuous path or a cycle. Again, cycle is again a kind of a path, but the difference is that you can repeat it many times as you like. And we are trying to visit each edge just once. For instance, me try to do it on this one. If I start, this is a starting point. If I continue like this, and to here, I'm not actually removing my hands. This is another one. But as you see, I cannot do it without stopping extrusion, and then I cannot have a continuous path. So here I need to stop the extrusion, go to another point here, and then have another set of, let's say, printing. So I couldn't do it with a single motion. Now, can I do it with this one? It's a bit more complicated. Actually, Euler has a theorem about this one, and it's named as Eulerian path. It states that you can have a kind of an Euler path if your vertices in this graph have an even degree, which means that at each vertex you should have 2 or, let's say, even number of edges coming out of this vertex. 2 times, let's say, n number of edges should be going out of this vertex. If that's the case, then we can say that there is an Eulerian circuit. We have a cycle in this circle, in this graph. Let's go back to our example here. If you look at the first example, we have 5 number of edges, 3 once again, and 3. So which means that we cannot have an Eulerian path, right? But if you look at here, we have 4, we have 2 degree, 4, another 4 here, 4 here, 4 here. So it's satisfying the requirement of Eulerian paths, which means that we can find a kind of a cycle going through these edges just once, and we can do it with a single motion. We don't need to remove our hand and jump to another point. So we can say that this has an Eulerian circuits. So what we have done in the study is that if you go back to our Voronoi example, and if you remember our discussions in the Voronoi chapter, we said that if the points are in general position, which means that they shouldn't be collinear, any 4 points, any 3 points shouldn't be collinear, or I think we discussed about a circle. If you don't have a circle having, let's say, 4 Voronoi sides on the perimeter, if that's the case, you can say that these sides are in general position, and if that's the case, we'll always have vertices with degrees of 3, right? Look at here, 3, again 3, 3, 3. Since this is a part of C1, so it's a polygon itself. We have a vertex here. Again, it has a degree of 3. So what do you think? Can we have an Eulerian path here, Eulerian circuit? Obviously, no, since the Eulerian states that we should have even number of edges at each vertex. But in the Voronoi diagram, we have the reverse. We always have odd number of vertices. But what about multiplying this Voronoi diagram with 2? Which means that I have 2 edges for all the, let's say, edges of the Voronoi diagram. So what will be the degree of each vertex? It will be multiplied by 2, as you see here. You will always have 6 number of edges at each vertex, and in that case, we will have even number of edges, even degree for all the vertices, and you can obtain an Eulerian path, Eulerian circuit for the motion which goes through the edges of the Voronoi diagram. But the thing is that this time we will be passing through each edge twice. This is the important part. We are going through these edges twice, and that's why while printing actually this one, I decreased the amount of extruded material while passing through these edges, so that at the end of the fabrication I would have the same amount of material set by the user. So this is our algorithm and how to obtain the Eulerian paths. So how do we start? We have an empty list as output, and that list will be giving us the printing path, and our algorithm accepts an edge of an, let's say, you have a kind of an Voronoi diagram. You may have many cycles. So you may start with an edge E, and that is the cycle C, and you also have the set of actually cycles. And what we do, we give these inputs and then start running this algorithm. We mark this edge E, and also C is marked, and then we add this edge to our output list E, and then we define another co-edge, which will be the reverse of our edge E, and then we continue by simply visiting all the cycles, and that will actually, I'm not going to discuss the details, but the thing is that you'll be calling the same function once again. So this is a recursive function, a very simple one, as you see. Just in 11 steps, you can complete this algorithm. And you need to run the same function once again, while if you come up with a Neve cycle, Neve, let's say, polygon, if these are not marked, then you will call them. And after you visit all the cycles, all the cells here, you will be doing a kind of a reverse operation and visit all the edges twice. These are actually how the things are done. You start with an C1 and E, then C1 is marked. We continue from E, and since we have a new edge, E prime, and this C prime is not marked, so we need to go into this cycle or cell and continue on with our case. As I said, I'm not going to discuss the details. If you are interested, there's a paper about it, and you can learn the fundamentals. So we said that the continuity is highly important, as in the case of previous example paper study. We try to find a way to have a continuous pattern, and this is an example for that also. You see there's a box or a square here. Initially, if you generate some kind of a pattern here, you need to start it here and add at the center of the square, which means that you need to go to the starting point after this is over. But instead of having such a case, you may also have modified a little bit so that you have a kind of a circuit. You see now it started at this point, and you can also add at this point. Or since it's a circuit, you may start here and end at this same point. Let's say you continue here, and then you will finish this path at the same point, since it's a circuit. And you can see the quality between these two cases. And as far as remember, they use the same algorithm for different slices and obtains nice results. Now we will switch to a different additive manufacturing technology. This is called as selective laser sintering. Some fundamentals are similar with fixed flame fabrication, but there are also differences. First of all, this one is performed in a powder bed. You will see what a powder bed is in a moment. Another thing, they will be using kind of a laser here. And another thing, another difference is that they are using powders of different materials. And these powders will be spread on the table, and then they will be joined together with the help of the laser above. And our table will go down after one layer is okay. And in the next layer, some amount of powder will be once again spread on the table, and again the powders will be sintered. So this is a sintering operation. The powders are not melted, they are sintered together. But we also have SLM, which is a very similar version, selective laser melting. In that case, they are melting these powders, but we will see now selective laser sintering. Slicing is performed in CAM software. So we have part cylinder, this is going downwards. Part piston mobility. Roller assembly is responsible for spreading the powder on the table, and this is called image projection, but it's kind of a laser. You see this is spreading powder, and then this dark blue regions are sintered, but the rest of the powders are still inside the bed, and they are acting as support structures. If it was a fused flame fabrication process, we would need support structure underneath this region. But since this is fabricated inside a powder bed, the powders, these blue regions, will act as a support structure, and they will help you keep these centered powders in place. So you don't need to have special support structures. that's all for the animation. Let me go through once again a different schematic. In here, we have an extra platform. This is called as powder supply or some kind of powder, raw powder, let's say piston. This is part piston or wheel platform. This is going downward, but this part is going upward, so that you have extra powder at this level, and this extra powder will be spread with the help of leveling roller. And this one, as you see, going to right, and it's also rotating. And with the help of the laser, these powders are sintered together. And the remaining powder inside this bed is actually not sintered, but probably have undergone some temperature increase. You may use some of the powders inside the bed, but not completely. There are different recycling systems depending on your equipment. You may try to recycle some of the powders inside the bed, but the most important thing is that you don't need to have special support structures in the selective laser sintering systems. And another difference with respect to the fistula fabrication is that you don't need to have considered about various infill patterns or infill percentage. For every part, you'll have solid interior. So the interior of the part should be sintered in 100%. You shouldn't have any gap, any, let's say, void inside the part. And this is obviously easier than the pad planning is easier than fistula fabrication, since you don't need to worry about the interior structure and worry about the support structure. They are not valid in this selective laser sintering process. Any questions, guys? Actually, the pad planning of SLS systems are very similar to robot motion planning or some agricultural robots motion planning. You see, we have a kind of a slice here. Assume that this field is an example of a slice, and we have some holes here. You see, and with the help of our, let's say, kind of field vehicle, we try to cover the whole region. And this is also the same for selective laser sintering. We have a kind of a shell again, one or two shells, and then the rest is actually covered with some simple zigzag patterns. And again, we are trying to find as continuous paths as possible. We try to eliminate any discontinuities in the interior of your part. Any questions, guys, regarding SLS systems, selective laser sintering methods? Okay, and if you don't have any questions, we can switch to selective laser sintering. I'm sorry, selective stereolithography. This is the abbreviation of it, stereolithography, and this is a desktop printer utilizing actually this technology. You'll see a very brief video about it, and the difference is that they are using liquid material. They are using thermoset material. It's in resin form, and again, with the help of laser, this resin is solidified. Actually, not totally solidification; it's an polymerization. Photopolymerization process is carried out, and we convert these liquid resin into solid products. Oh, I'm sorry, guys. You see, this is a CAM software of an SLA system, and the difference with respect to the previous one is that they prefer to use support structures. Since this is not manufactured inside a powder bed, for complicated shapes, for overhanging regions, we need to have support structures. So you may may see some light downside here. This is laser actually, and they are printing the product upside down. And with the help of this laser, the light source, we can start the polymerization process and make them solid. Inside this vat, we have liquid material. With the help of the laser, they are polymerized and we have solid products. Now, post-processing support structures are removed and it's ready to use. It's obviously made for prototyping. We have a similar schematic here. We only have a single platform in this manufacturing technique. In the SLS systems, we may have two of them. One is going down, one is going up, but in stereolithography, we only have a single platform. In this configuration, it's going upward, but there are also configurations where your build platform is going downward. The thing is that you should start with liquid material, resin. It's inside a tank, and underneath the system, we have a laser. And with the help of the mirror, this laser is reflected on the table, and the regions which are actually under the exposure of laser beam will be polymerized, and you'll have solid regions. And again, as I said while we were watching the video, we need to have support structures for critical parts for overhanging regions. So this is the abbreviation, SLA, and the long form is stereolithography. We are making use of laser, as in the case of selective laser sintering. In the SLS, we don't have support structures, but in SLA and in fused filament fabrication systems, we need to have support structures. And another similar property with respect to SLS is that the interior is solid. So the thing is that your laser again should cover the interior of your slices completely. You cannot have 20%, 50% infill. The interior should be filled completely. And it's a bit complicated process than SLS, since we need to have support structure. You need to spend some time for determining the support structure regions and the type of them. Here you see some examples. These days, people are trying to find some special support structures where you use less material. In the previous case, as you see, they have pure columns, but now they have kind of tree-like structures and obviously use less material.